Stanford University.
Yeah, hello everyone. Welcome to CS 231N. I'm Song Han. Today I'm going to give a guest lecture on the efficient methods and hardware for deep learning. So I'm a fifth-year PhD candidate here at Stanford, advised by Professor Bill Daly. So in this course, we have seen a lot of convolution neural networks, recurrent neural networks, or even just last time, the reinforcement learning. They are spanning a lot of applications, for example, the self-driving car, machine translation, AlphaGo, and smart robots. It is changing our lives, but there is a recent trend that in order to achieve such high accuracy, the models are getting larger and larger. For example, for ImageNet recognition, the winner from 2012 to 2015, the model size increased by 16x. And just in 1 year, for Baidu's deep speech, just in 1 year, the training operations, the number of training operations increased by 10x. So such large model creates lots of problems. For example, the model size becomes larger and larger, so it's difficult for them to be deployed either on those, for example, on the mobile phones. If the item is larger than 100 megabytes, you cannot download until you connect to Wi-Fi. So those product managers in, for example, Baidu, Facebook, they are very sensitive to the size of the binary size of their model. And also, for example, the self-driving car, if you want to do those on over-the-air update for the model, if the model is too large, it's also difficult. And the second challenge for those for those large models is that the training speed is extremely slow. For example, the ResNet 152, which is only less than 1% actually, more accurate than ResNet 101, takes 1.5 weeks to train on 4 Maxwell M40 GPUs, for example, which greatly limits the either we are doing homework or the researchers designing new models is getting pretty slow. And the third challenge for those bulky models is the energy efficiency. For example, the AlphaGo beating Li Soudou last year took 2,000 CPUs and 300 GPUs, which costs $3,000 just to pay for the electric bill, which is insane. So either on those embedded devices, those models are draining your battery power, or on the data center, it increases the total cost of ownership of maintaining a large data center. For example, Google, in their blog, they mentioned if all the users using the Google Voice search for just 3 minutes, they have to double their data center. So that's a large cost. So reducing such cost is very important. And let's see where is actually the energy consumed. The large model means lots of memory access. You have to load those models from the memory, means more energy. If you look at how much energy is consumed by loading the memory versus how much is consumed by multiplications and add those arithmetic operations, the memory access is more than two or three orders of magnitude more energy consuming than those arithmetic operations. So how to make deep learning more efficient? So we have to improve the energy efficiency by this algorithm and hardware co-design. So this is the previous way we design hardware. For example, we have some benchmark, say spec 2006, and then run those benchmarks and tune your CPU architectures for those benchmarks. Now what we should do is to open up the box to see what can we do from the algorithm side first, and see what is the optimum question mark processing unit that breaks the boundary between the algorithm hardware code between algorithm hardware to improve the overall efficiency. So today's talk, I'm going to have the following agenda. We are going to cover 4 aspects: the algorithm and hardware, inference and training. So they form a small 2x2 matrix. So includes the algorithm for efficient inference, hardware for efficient inference, and the algorithm for efficient training, and lastly, the hardware for efficient training. For example, I'm going to cover the TPU, I'm going to cover the Volta. But before I cover those things, let's have 3 slides for hardware 101. a brief introduction of the families of hardware in such a tree. So in general, we can have roughly 2 branches. One is general purpose hardware. It can do any applications versus the specialized hardware, which is tuned for a specific kind of applications, a domain of applications. So the general purpose hardware includes the CPU or the GPU. And their difference is that CPU is latency oriented, single threaded. It's like a big elephant. While the GPU is throughput oriented. It has many small weak threads, but there are thousands of such small weak cores, like a group of small ants, but there are so many ants. And specialized hardware, roughly, there are FPGAs and ASICs. So FPGA stands for Field Programmable Gate Array. So it is programmable, hardware programmable. Those logic can be changed. So it's cheaper for you to try new ideas and do prototype, but it's less efficient. It's in the middle between the general purpose and pure ASIC. So ASIC stands for application-specific integrated circuit. It has a fixed logic, just designed for a certain application, for example, deep learning. And Google's TPU is a kind of ASIC. And the neural networks we train on the NVIDIA GPUs is here. And another slide for hardware 101 is the number representations. So in this slide, I'm going to convey you the idea that all the numbers in computer are not represented by a real number. It's not a real number, but they are actually discrete. Even for those floating point, using 32-bit floating point numbers, the resolution is not perfect. It's not continuous, but it's discrete. So for example, FP32, meaning using 32-bit to represent the floating point number. So there are 3 components in the representation: the sign bit, exponent bit, the mantissa. And the number it represents is shown by -1 to the s times 1.m times 2 to the exponent. So similarly, there is FP16 using 16-bit to represent the floating point number. So in particular, I'm going to introduce int8, where the Google TPU using a integer to represent a fixed point number. So we have a certain number of bits for the integer, followed by a radix point, different for different layers, and lastly, the fractional bits. So why do we prefer those 8-bit or 16-bit rather than those traditionally the 32-bit floating point? That's the cost. So I generated a figure from 45 nanometer technology about the energy cost versus the area cost for different operations. In particular, let's see here, going from 32-bit to 16-bit, we have about 4 times reduction in energy, and also about 4 times reduction in the area. Area means money. Every millimeter square takes money to tape out a chip. So it's very beneficial for hardware design to go from 32-bit to 16-bit. That's why you hear about the NVIDIA from Pascal architecture later. They're starting to support FP16. That's the reason why it's so beneficial. For example, previously the battery can last 4 hours. Now it becomes 16 hours. That's what it means to reduce the energy cost by 4 times. But here, still, there's the problem of large energy cost for reading the memory. And let's see how can we deal with this memory reference. So expensive, how do we deal with this problem later? So let's switch gear and come to our topic directly. So let's first introduce algorithm for efficient inference. So I'm going to cover 6 topics. This is a really long slide. So I'm going to go relatively fast. So the first idea I'm going to talk about is pruning. Pruning the neural networks. For example, this is the original neural network. So what I'm trying to do is, can we remove some of the weights, and still have the same accuracy? It's like pruning a tree, get rid of those redundant connections. This is first proposed by Professor Yang Kong back in 1989, and I revisited this problem in 26 years later on those modern deep neural nets to see how it works. So not all parameters are useful, actually. For example, in this case, if you want to fit a single line, but you're using a quadratic term, apparently the 0.01 is redundant parameter. So I'm going to train the connective first, and then prune some of the connections, and train the remaining weights, and do this process iteratively. And as a result, I can reduce the number of connections in AlexNet from 60 million parameters to only 6 million parameters, which is 10 times less the computation. So, so this is the accuracy. So the x-axis is how much parameters do you prune away, and the y-axis is the accuracy you have, right? So we want to have less parameters, but we also want to have the same accuracy as before. We don't want to sacrifice the accuracy. For example, at 80%, we knock zero away 80% of the parameters, but the accuracy dropped by 4%. That's intolerable. But the good thing is that if we retrain the remaining weights, the accuracy can fully recover here. And if we do this process iteratively by pruning and retraining, we can fully recover the accuracy not until we prune away 90% of the parameters. So if you go back to home and try on your IPython notebook, just zero away 50% of the parameters, say in one of your homeworks, you will astonishingly find that the accuracy actually doesn't hurt. So we just mentioned convolution neural nets. How about RNNs and LSTMs? So I tried with this neural talk. Again, pruning away 90% of the weights doesn't hurt the blue score. And here are some visualizations. For example, the original picture, the neural talk says, a basketball player in a white uniform is playing with a ball, versus pruning away 90%. It says, a basketball player in a white uniform is playing with a basketball. And on and so on. But if you're too aggressive, right? If you're too aggressive, say you prune away 95% of the weights, the network is going to get drunk. It says, a man in a red shirt and white and black shirt is running through a field. So there's really a limit, a threshold you have to take care of during the pruning. So interestingly, after I did work, I did some literature research and find actually the same pruning procedure actually happened to human brain as well. So when we were born, there are about 50 trillion synapses in the brain. And at 1 year old, this number surged to 1,000 trillion. And as we become an adolescent, it becomes smaller actually, 500 trillion in the end, according to the study by Nature. So this is very interesting. And also the pruning changed the weight distribution because we are removing those small connections. And after we retrain them, that's why it becomes soft in the end. Yeah, so the question is, how do we deal with those zero connections? So we force them to be zero in all the SGD iterations. Yep. Question? Yeah, so very simple. Small weights, drop it, sort it. If it's small, just okay. Yeah. So the next idea, weight sharing. So now we have, remember our end goal is to remove connections and so that we can have less memory footprint, so that we can have more energy efficient deployment, right? Now we have less number of parameters by pruning. What we want to have is less number of bits per parameter. So they multiply together, they get a small model, right? So the idea is like this. Not all numbers, not all the weights has to be the exact number. For example, 2.09, 2.12, or all these 4 weights, you just put them using 2 to represent them. That's enough. Otherwise, too accurate numbers just leads to overfitting. So the idea is I can cluster the weights if they are similar, just using a centroid to represent the number instead of using the full precision weight. so that every time I do the inference, I just do inference on this single number. For example, this is a 4x4 weight matrix in a certain layer, right? And what I'm going to do is do k-mean clustering by having the similar weights sharing the same centroid. For example, 2.09, 2.12, I store an index of 3 pointing to here. So that the good thing is we need to only store the 2-bit index rather than the 32-bit floating point number. That's 16 times saving. 16 times saving. And how do we train such neural network? They are binded together, right? So after we get the gradient, we color them in the same pattern as the weight. And then we do a group by operation by having all the weights with the same index grouped together. And then we do a reduction by summing them up. And then multiplied by the learning rate subtracted from the original centroid. That's one iteration of the SGD for such weight shared neural network. So remember previously after pruning, this is what the weight distribution like. And after weight sharing, they become discrete. There are only 16 different values here, meaning we can use 4 bits to represent each number. And by training on such weight shared neural network, right? Training on such weight shared neural network, these weights can adjust. You know, it is these subtle changes that compensated for the loss of accuracy. So let's see. This is the number of bits we give it. This is the accuracy. For convolution layers, not until 4 bits does the accuracy begin to drop. And for those fully connected layers, very astonishingly, 2 bits, not until 2 bits, only 4 numbers, does the accuracy begins to drop. And this result is per layer. So we have covered 2 methods, right? Pruning and weight sharing. What if we combine these 2 methods together? Do they work well? So by combining these methods, this is the compression ratio, the smaller the better on the left, and this is the accuracy. We can combine it together and make the model about 3% of its original size without hurting the accuracy at all. Compared with the each working individually by 10%, the accuracy begins to drop. And compared with the cheap SVD method, it have a better compression ratio. And the final idea is we can apply those Huffman coding to use more number of bits for those infrequent numbers, infrequently appearing weights, and less number of bits for those more frequently appearing weights. So by combining these 3 methods, pruning, weight sharing, and also Huffman coding, we can compress the neural networks, state-of-the-art neural networks, ranging from 10x to 49x, 10x to 49x, and without hurting the prediction accuracy. Sometimes a little bit better, but maybe that is noise. So the next question is, these models are just pre-trained models by, say, Google, Microsoft. Can we make a compact model, compact model to begin with, even before such compression? So SqueezeNet, you may have already worked with this neural network model in a homework. So that's the idea is we are having a squeeze layer here to shield the 3x3 convolution with fewer number of channels. So that's where squeeze come from. And here we have 2 branches rather than 4 branches as in the exception model. So as a result, the model is extremely compact. It doesn't have any fully connected layers. Everything is fully convolutional. The last layer is a global pooling. So what if we apply the deep compression algorithm on such already compact model? Will it be getting even smaller? Okay, so this is AlexNet after compression. This is SqueezeNet. Even before compression, it's 50x smaller than AlexNet, but has the same accuracy. After compression, 510x smaller. but the same accuracy, only less than half a megabyte, less than half a megabyte. This means it's very easy to fit such a small model on the cache, on the L3 cache, which is usually tens of megabytes SRAM. So what does it mean? It's possible to achieve speedup. So this is the speedup I measured for these fully connected layers only for now. Fully connected layers only for now. On the CPU, GPU, and the mobile GPU, before pruning and after pruning the weights. And on average, I observed 3x speedup on the CPU, about 3x speedup on the GPU, and roughly 5x speedup on the mobile GPU, which is a TK1. And so is the energy efficiency. In an average improvement from 3x to 6x on the CPU, GPU, and mobile GPU. And these ideas are used in these companies. Okay, having talked about weight pruning and weight sharing, which is a nonlinear quantization method, I'm going to talk about quantization, which is widely used in the TPU design. All the TPU design is using only 8-bit, or 8-bit for inference. And the way how they can use that is because of the quantization. And let's see how does it work. So quantization has, this is a complicated figure, but the intuition is very simple. You run the neural network and train it with the normal floating point numbers, and quantize the weight and activations by gather the statistics for each layer. For example, what is the maximum number, and how many bits are enough to represent this dynamic range. Then you use that number of bits for the integer part, and the rest of the 8-bit or 7-bit for the other part of the 8-bit representation. And also we can fine-tune in the floating point format, or we can also use feed-forward with fixed point and back propagation weight update with the floating point number. There are lots of different ideas to have better accuracy. And this is the result for the number of bits versus what is the accuracy. For example, using fixed 8-bit, the accuracy for GoogleNet doesn't drop significantly. And for VGG16, it also remains pretty well for the accuracy. Well, if you're going down to 6-bit, the accuracy begins to drop pretty dramatically. Okay, next idea, low-rank approximation. Low-rank approximation. It turned out that for a convolution layer, you can break it into 2 convolution layers. One convolution here followed by a 1-by-1 convolution. So that it's like you break a complicated problem into 2 separate small problems. This is for convolution layer. As we can see, achieving about 2x speedup, there is almost no loss of accuracy. And achieving a speedup of 5x, roughly 6% loss of accuracy. And this also works for fully connected layers. The simplest idea is using the SVD to break it into one matrix into 2 matrices. And follow this idea, this paper proposes to use the tensor train to break down one fully connected layer into a train, lots of fully connected layers. That's why it's called a train. Okay. So going even more crazy, can we use only 2 bits, two weights or 3 weights to represent a neural network, a ternary weight or a binary weight? We already seen this distribution before after pruning, right? There are some positive weight, some negative weight. Can we just use 3 numbers? Just use 1, -1, 0 to represent the neural network. And this is our recent paper at Clear that we maintain a full precision weight during training time, but at inference time, we only keep the scaling factor and the ternary weight. So during inference, we only need 3 weights. That's very efficient and making the model very small. And this is the proportion of the positive 0 and negative weights. They can change during the training. So is their absolute value. And this is the visualization. The visualization of the kernels by this trained ternary quantization. we can see some of them are maybe a corner detector, like here, and also here. Some of them are maybe edge detector, for example, this filter. Some of them are corner detector, like here, this filter. Actually, we don't need such fine-grained resolution, just 3 weights are enough. So this is the validation accuracy on ImageNet with the AlexNet. So the dashed line is the baseline accuracy with floating point 32. And the red line is our result. Pretty much the same accuracy converged compared with the full precision weights. Okay, last idea, WINOGRAD transformation. So this is about how do we implement deep neural nets? How do we implement the convolutions? So this is the conventional direct convolution implementation method. The slide credit to Julian, a friend from NVIDIA. So originally we just do the element-wise, do a dot product for those 9 elements in the filter and 9 elements in the image, and then sum it up. So for example, for every output, we need 9 times C number of multiplication and adds. WINOGRAD convolution. WINOGRAD convolution is another method, equivalent method. Equivalent method is not lossy, it's equivalent method. Proposed first in this paper, fast algorithm for convolution neural networks, that instead of directly doing the convolution, move it one by one, it first transforms the input feature map to another feature map, which contains only, the weight contains only 0.52 that can be efficiently implemented with shift, and also transform the filter into a 4x4 tensor. So what we are going to do here is sum over C and do a element-wise product. So there are only 16 multiplications happening here. And then we do an inverse transform to get 4 outputs. So the transform and the inverse transform can be amortized, and the multiplication over there can be ignored. So in order to get 4 output, we need 9 times channel times 4, which is 36 times channel multiplications originally for the direct convolution. But now we need 16 times C for 4 outputs, 16 times number of channels for 4 outputs. So that is 2.25x less number of multiplications to perform the exact same multiplication. And here is the speed up, 2.25x. So theoretically 2.25x speed up. And in real, so from cuDNN5, they incorporated such WINOGRAD convolution algorithm. This is on the VGGNet, I believe. The speed up is roughly 1.7 to 2x speed up, pretty significant. And after cuDNN5, the cuDNN begins to use the WINOGRAD convolution algorithms. Okay, so so far we have covered those efficient algorithms for efficient inference, right? We covered pruning, weight sharing, quantization, and also WINOGRAD, binary, ternary. So now let's see what is the optimal hardware. Let's see what is the optimal hardware for those efficient inference. And what, for example, what is a Google TPU? So there are a wide range of domain-specific architectures, or ASICs, for deep neural networks. They have a common goal is to minimize the memory access, to save the power. For example, the Iris from MIT, by using the row stationary data flow to minimize the off-chip DRAM access. And Dadiannao from China Academy of Science buffered all the weights on the on-chip DRAM instead of having to go to off-chip DRAM. So the TPU from Google is using 8-bit integer to represent the numbers. And at Stanford, I proposed the EIE architecture that support those compressed and sparse deep neural network inference. So this is what the TPU looks like. It's actually smartly can be put into the disk drive, up to 4 cars per server. And this is the high-level architecture for the Google TPU. Don't be overwhelmed. It's actually the kernel part here is this giant matrix multiplication unit. So it's a 256 by 256 matrix multiplication unit. So in one single cycle, it can perform 64 kilo, those number of multiplication and accumulate operations. So running at 700 megahertz, the throughput is 92 teraflops per second. Teraops per second because it's actually integer operation. So which is about 25x as GPU and more than 100x as the CPU. And notice TPU has a really large software managed on-chip buffer. It is 24 megabytes. The CPU, the memory for the CPU, the cache for the CPU, the L3 cache is usually 16 megabytes. This is 24 megabytes, which is pretty large. And it's powered by 2 DDR3 DRAM channels. So this is a little weak because the bandwidth is only 30 gigabytes per second, compared with the most recent GPU, the HBM, 900 gigabytes per second. But that is back in, DDR4 is released in 2014. So that makes sense because the design is a little, during that day, use the DDR3. But if you're using DDR4 or even high bandwidth memory, the performance can be even boosted. So this is a comparison about Google's TPU compared with the CPU, GPU, this K80 GPU, by the way, and the TPU. So the area is pretty much smaller, like half the size of a CPU and GPU. And the power consumption is roughly 75 watts. And you see this number, the peak teraops per second is much higher than the CPU and GPU. It's about 90 teraops per second, which is pretty high. So here is a workload, thanks to David sharing the slide. This is the workload at Google. They did the benchmark on these TPUs. So it's a little interesting that convolution neural nets only account for 5% of the data center workload. Most of them is multi-layer perceptron, those fully connected layers, about 61%, maybe for ads, I'm not sure. And about 29% of the workload in data center is the long short-term memory, for example, speech recognition or machine translation, I suspect. Yeah. So in order, remember just now we have seen they are 90 teraops per second. But what actually number of teraops per second can be achieved? So this is a basic tool to measure the bottleneck of a computer system, whether you are bottlenecked by the arithmetic or you are bottlenecked by the memory bandwidth. It's like if you have a bucket, the lowest bar of the bucket determines how much water you can hold in the bucket. So in this region, you are bottlenecked by the memory bandwidth. So the x-axis is the arithmetic intensity, which is number of floating point operations per byte, the ratio between the computation and the memory bandwidth overhead. So the y-axis is the actual attainable attainable performance. Here is the peak performance, for example, the peak performance. When you do a lot of operation after you fetch a single piece of data, if you can do a lot of operation on top of it, then you are bottlenecked by the arithmetic. But after you fetch a lot of data from the memory, but you just do a tiny little bit of arithmetic, then you will be bottlenecked by the memory bandwidth. So how much you can fetch from the memory determines how much real performance you can get. And remember, there is a ratio when it is 1 here. This region, it happens to be the same as the turning point, is the actual memory bandwidth of your system. So let's see, what is it like for the TPU? The TPU's peak performance is really high, about 90 TOPS per second. For those convolution nets, they are pretty much saturating the peak performance. But there are lots of neural networks that has a utilization less than 10%, utilization of less than 10%, meaning that 90 TOPS per second is actually you actually achieve about 3 to 12 TOPS per second in real case. But why is it like that? The reason is, in order to have those real-time guarantee, let the user not to wait for too long, you cannot batch a lot of users' images or speech voice data at the same time. So as a result, for those fully connected layers, they have very little reuse. So they are bottlenecked by the memory bandwidth. For those convolution neural nets, for example, this blue one that achieved 86, which is CNN0. Let's see, CNN0, the ratio between the ops and the number of memory is the highest, right? It's pretty high, 2,000, more than 2,000, compared with other multi-layer perception or long short-term memory. The ratio is pretty low. So this figure compares this is the TPU, and this one is the CPU, this is the GPU. Here is the memory bandwidth, the peak memory bandwidth at a ratio of 1 here. So GPU has the highest memory bandwidth. And here is where are these neural networks lie on this curve. So the asterisk is for the TPU. It's still higher than other dots. But if you're not comfortable with this log scale figure, this is what it's like put it in linear scale, the linear roofline. So pretty much everything disappeared except for the TPU results. So still, all these lines, although they are higher than the CPU and GPU, it's still way below the theoretical peak bandwidth, peak floating point, peak operations per second. So as I mentioned before, it is really bottlenecked by the low latency requirement so that you can have a large batch size. So that's why you have low operations per byte. And how do you solve this problem? You want to have less number of memory footprint so that you can reduce the memory bandwidth requirement. So you need to compress. One solution is to compress the model. And the challenge is, how do we build a hardware that can do inference directly on the compressed model? So I'm going to introduce my design of EIE, the efficient inference engine, which deals with those sparse and compressed model to save the memory bandwidth. And the rule of thumb, like we mentioned before, is taking advantage of sparsity first. Anything times 0 is 0. So don't store it, don't compute on it. And second idea is this kind of, you don't need that much of full precision, but you can approximate it. So by taking advantage of the sparse weight, we get about 10x saving in the computation, 5x less memory footprint. The 2x difference is due to the index overhead. And by taking advantage of the sparse activation, meaning after redo, if the activation is 0, then ignore it. You save another 3x the computation. And by such weight sharing mechanism, you can use 4 bits to represent each weight rather than 32 bits. That's another 8 times saving in the memory footprint. So this is logically how the weights are stored, a matrix by 4 by 8 matrix, and this is how physically they are stored. Only the non-zero weight are stored. So you don't need to store those zeros. You save the bandwidth fetching those zeros. And also I'm using the relative index to further save the number of memory overhead. So in the computation, like this figure shows, we are running the multiplication only on non-zeros. If it's 0, then skip it. Only broadcast it to the non-zero weights. And if it is 0, skip it. If it's a non-zero, do the multiplication. In another cycle, do the multiplication. So the idea is anything multiplied by 0 is 0. So this is a little complicated. I'm going to go very quickly. I'm going to have a lookup table that decode the 4-bit weight into the 16-bit weight. And using the 4-bit relative index, pass it through an address accumulator to get the 16-bit absolute index. And this is what the hardware architecture like in the high level. You can feel free to refer to my paper for detail. Okay, speed up. So using such efficient hardware architecture and also model compression, this is the original result we have seen for CPU, GPU, and mobile GPU. Now EIE is here, 189 times faster than the CPU, and about 13 times faster than the GPU. So this is the energy efficiency on the log scale. It's about 24,000x more energy efficient than the CPU, and about 3,000x more energy efficient than the GPU. It means, for example, previously, if your battery can last for 1 hour, now it can last for 3,000 hours, for example. So if you say ASIC is always better than CPU and GPUs because it's customized hardware. So this is comparing EIE with the peer ASICs, for example, 大电脑 and the True North. It has a better throughput, better energy efficiency by an order of magnitude compared with other ASICs, not to mention the CPU, GPU, and FPGAs. Okay, so we have covered half of the journey. We mentioned inference. We pretty much covered everything for inference. Now we are going to switch gear and talk about training. How do we train neural networks efficiently? How do we train it faster? So again, we are starting with the algorithm first, efficient algorithms, followed by the hardware for efficient training. So for efficient training algorithms, I'm going to mention 4 topics. The first one is parallelization, and then mixed precision training, which is just released about 1 month ago at NVIDIA GTC, so it's fresh knowledge. And then model distillation, followed by my work on Dense-Sparse-Dense training, or better regularization technique. Okay, so let's start with parallelization. So this figure shows, if you're in the hardware community, you must be very familiar with this figure. So as the time goes by, what is the trend for the number of transistors is keeping increasing. But the single-threaded performance is getting plateaued in recent years. And also the frequency is getting plateaued in recent years because of the power constraint, the stop-up did not scaling. And the interesting thing is the number of cores is increasing. So what we really need to do is the parallelization. How do we parallelize the problem to take advantage of parallel processing? Actually, there are a lot of opportunities for parallelism in deep neural networks. For example, we can do data parallel. For example, feeding two images into the same model and run them at the same time. This doesn't affect the latency for a single input. It doesn't make it shorter, but it makes batch size larger. Basically, if you have 4 machines, your effective batch size becomes 4 times as before. So it requires the coordinated weight update. For example, this is a paper from Google. there is a parameter server. There's a parameter server as a master and a couple of slaves running their own piece of data, of training data, and update the gradient to the parameter server and get the updated weight for them individually. That's how data parallelism is handled. Another idea is there could be a model parallelism. You can split your model and handle it to different processors or different threads. For example, this is the image. This is the image. You want to run convolution on this image, like this six-dimension for loop. What you can do is you can cut the input image by 2 by 2 blocks so that each thread or each processor handles 1/4 of the image. Although there is a small halo here in between, you have to take care of. And also, you can parallelize by the output or input feature map. And for those fully connected layers, how do we parallelize the model? It's even simpler. You can cut the model into half and handle it to different threads. And the third idea, you can even do hyperparameter parallel. For example, you can tune your learning rate, your weight decay on different machines for those coarse-grained parallelism. So there are so many alternatives you have to tune. Okay, small summary of the parallelism. So there are lots of parallelisms in deep neural networks. For example, the data parallelism. You can run multiple training images, but you cannot have a limited number of threads or processors because you're limited by batch size. If it's too large, stochastic gradient descent becomes gradient descent. That's not good. And you can also run the model parallelism, split the model either by cutting the image or cutting the weight, convolution weights. Maybe just now I give a small, oh yeah, so never mind. Either cutting the image or cutting the fully connected layers. So it's very easy to get 16 to 64 GPUs training one model in parallel, having very good speedup, almost linear speedup. Okay, next interesting thing, mixed precision with FP16 or FP32. So remember in the beginning of this lecture, I have a chart showing the energy and area overhead for FP 16-bit versus 32-bit. Going from 32-bit to 16-bit, you save about 4x the energy and 4x the area, right? So can we train a deep neural network with such low precision with floating point 16-bit rather than 32-bit? It turned out we can do that partially. By partially, I mean we need FP32 in some places. And where are those places? So we can do the multiplication in 16-bit as input. And then we have to do the summation in 32-bit accumulation. And then convert the result to 32-bit to store the weight. So that's where the mixed precision comes from. So for example, we have a master weight stored in floating point 32. We down convert it to floating point 16, and then we do the feed forward with 16-bit weight, 16-bit activations. We get a 16-bit activation here in the end. When we are doing back propagation, all the computation is also done with floating point 16-bit. Very interesting here, for the weights, we get a floating point 16-bit gradient here for the weight, 16-bit gradient for the weight. But when we are doing the update, so W times learning plus learning rate times the gradient, that operation has to be done in 32-bit. That's where the mixed precision coming from. You see there are two colors, which here is 16-bit, here is the 32-bit. That's where the mixed precision come from. So does such low precision sacrifice your prediction accuracy for your model? So this is the figure from NVIDIA. I just released a couple of weeks ago, actually. thanks to Paulius giving me the slide. The convergence between floating point 32 versus the Volta tensor op, which is basically the mixed precision training, are actually pretty much the same for convergence. If you zoom it in a little bit, they are pretty much the same. And for ResNet, the mixed precision sometimes behave a little better than the full precision weight, maybe because of noise. But in the end, after you train the model, this is result for AlexNet, Inception V3, and ResNet 50 with FP32 versus the FP16 mixed precision training. The accuracy is pretty much the same for these two methods, a little bit worse, but not by too much. Okay, so having talked about the mixed precision training, the next idea is to train with model distillation. For example, you can have multiple neural networks, GoogleNet, VGGNet, ResNet, for example. And the question is, can we take advantage? Can we take advantage of these different models? Of course, we can do model ensemble, right? Can we utilize them as teacher? Utilize them as teacher to teach a small junior neural network to have it perform as good as the senior neural network. So this is the idea. So you have multiple large, powerful junior senior neural networks to teach this student model, and hopefully it can get better result. And the idea to do that is, instead of using this hard label, for example, for cow, dog, cat, the probability for dog is 100%, but the output of the geometric ensemble of those large teacher neural networks, maybe the dog has 90%, and the cat is about 10%. And the magic happens here. You want to have a softened result label here. For example, the dog is 30%, the cat is 20%. Still, the dog is higher than the cat. So the prediction is still correct. But you use this soft label to train the student neural network, rather than use this very hard label to train the student neural network. And mathematically, you control how much do you make it soft by this temperature during the softmax, controlling by this temperature. And the result is that starting with a trained model that classifies 58.9% of the test frames correctly, the new model converges to 57%, only trained on 3% of the data. So that's the magic for model distillation using this kind of soft label. And the last idea is my recent paper using a better regularization to train deep neural nets. We have seen these two figures before. We pruned the neural network, having less number of weights, but have the same accuracy. Now, what I did is to recover and retrain those weights shown in red and make everything train out together to increase the model capacity after it is trained at a low dimensional space. It's like you learn the trunk first and then gradually add those leaves and learn everything together. It turns out on ImageNet dataset, it performs relatively about 1% to 4% absolute improvement of accuracy. And it's also general purpose, works on long short-term memory and also recurrent neural nets collaborated with Baidu. So I also open sourced this better trained model on the DSD model zoo, where there are trained all these models, GoogleNet, VGG, ResNet, and also SqueezeNet, and also AlexNet. So if you are interested, feel free to check out these model zoo and compare it with the Cafe model zoo. Here are some examples on Dense-Sparse-Dense training helps with image capture. For example, this is a very challenging figure. The original baseline of NeuroTalk says a boy in a red shirt is climbing a rock wall. And the sparse model says a young girl is jumping off a tree, probably mistaken the hair with either the rock or the tree. But the Sparse-Dense training, by using this kind of regularization on the low dimensional space, it says a young girl in a pink shirt is swinging on a swing. And there are a lot of examples due to the limit of time. I will not go over them one by one. For example, a group of people are standing in front of a building, there's no building. A group of people are walking in the park. Feel free to check out the paper and see more interesting results. Okay, finally, we come to efficient hardware for efficient training. How do we take advantage of the algorithms we just mentioned? For example, parallelism, mixed precision. How are the hardware designed to actually take advantage of such features we can obtain? First, GPUs. This is the NVIDIA Pascal GPU, GP100, which was released last year. So it supports actually 20 teraflops on FP16. It has 16 gigabytes of high bandwidth memory. It's 750 gigabytes per second. So remember, computation and memory bandwidth are the two factors determines your overall performance. Whichever is lower, you will suffer. So this is really high bandwidth, 700 gigabytes. Compared with DDR3, it's just 10 or 30 gigabytes per second. Consumes 300 watts. And it's done in 16 nanometer process and have a 160 gigabytes per second NVLink. So remember, we have computation, we have memory, and the third thing is the communication. All three factors has to be balanced in order to achieve a good performance. So this is very powerful. But even more exciting, just about a month ago, Jensen released the newest architecture called Volta, the Volta GPUs. And let's see what is inside the Volta GPU. Just released less than a month ago. So it has 15 FP32 teraflops. And what is new here, there is 120 Tensor TOPS specifically designed for deep learning. And we'll later cover what is the Tensor Core and what is this 120 coming from. And rather than 750 gigabytes per second, this year, the HBM2, they're using 900 gigabytes per second memory bandwidth. Very exciting. And 12 nanometer process has a die size of more than 800 millimeters square, a really large chip, and supported by 300 gigabytes per second NVLink. So what's new in Volta? The most interesting thing for us, for deep learning, is this thing called Tensor Core. So what is a Tensor Core? Tensor Core is a unit, actually an instruction that can do the 4x4 matrix times a 4x4 matrix. The fused FMA stands for fused multiplication and add in this mixed precision operation just in one single clock cycle, one clock cycle. So let's decipher a little bit what does this mean. So mixed precision is exactly as we mentioned in the last chapter. So we are having FP16 for the multiplication, but for accumulation, we are doing it with FP32. That's where the mixed precision comes from. So you are, let's see how many operations it is. 4 by 4 by 4. It's 64 multiplications done just in one single cycle. That's 12x increase in the speedup of the Volta, or compared with the Pascal, which is released just last year. So this is the result for matrix multiplication on different sizes. The speedup of Pascal, of Volta over Pascal, it's roughly 3x faster doing these matrix multiplications. And what we care more is not only matrix multiplication, but actually running the deep neural nets. So both for training and for inference. And for training a Resident 50, by taking advantage of this Tensor Core in this V100, it is 2.4x faster than the P100 using FP32. So on the right-hand side, it compares compares the inference speedup given a 7 microsecond latency requirement. What is the number of images per second it can process? It is a measurement of throughput. Again, the V100, V100 over P100 by taking advantage of the Tensor Cores is 3.7 faster than the P100. So this figure gives roughly an idea what is a Tensor Core, what is an integer unit, what is a floating point unit. So this whole figure is is a single SM stream multiprocessor. So SM is partitioned into 4 processing blocks, 1, 2, 3, 4, right? And in each block, there are 8 FP64 cores here, and 16 FP32 and 16 INT32 cores here, units here. And then there are 2 of the new mixed precision tensor cores specifically designed for deep learning. And also there are the warp scheduler, dispatch unit, and register file as before. So what is new here is the Tensor Core unit here. So here is a figure comparing the recent generations of NVIDIA GPUs from Kepler to Maxwell to Pascal to Volta. We can see everything is keeping improving. For example, the boost clock has been increased from about 800 megahertz to 1.4 gigahertz. And from the Volta generation, there begins to have the Tensor Core units here, which has never existed before. And before the Maxwell, the GPUs are using the GDDR5, and then after the Pascal GPU, the HBM came into place, the high bandwidth memory, 750 gigabytes per second. Here, 900 gigabytes per second, compared with DDR3, 30 gigabytes per second. And the memory size actually didn't increase by too much. Memory size didn't increase by too much, and the power consumption is actually also remaining roughly the same. But given the increase of the computation, you can fit them in the fixed power envelope. That's still an exciting thing. And the manufacturing process is also improving from the 28 nanometer, 16 nanometer, all the way to 12 nanometer. And the chip area are also increasing to 800 millimeters square. That's really huge. So you may be interested in the comparison of the GPU versus the TPU, right? So how do they compare with each other? So in the original TPU paper, TPU actually designed roughly in the year of 2015, and this is comparison of the Pascal P40 GPUs released in 2016. So TPU, the power consumption is lower, has larger on-chip memory of 24 megabytes, really large on-chip SRAM managed by the software. And then both of them support int8 operations, while the inference per second given a 10 nanometer latency, the comparison for TPU is 1x, for the P40 is about 2x. So just last week, in the Google I/O, a new nuclear bomb is landed on the Earth. That is the Google Cloud TPU. So now TPU not only support inference, but also support training. So there's very limited information we can get beyond this Google blog. So the Cloud TPU delivers up to 180 teraflops to train and run machine learning models. And this is multiple Cloud TPU, making it into a TPU pod, which is built with 16, the second generation TPUs, and delivers up to 11.5 petaflops of machine learning acceleration. So in the Google blog, they mentioned that one of the large-scale translation models, the Google translation models, used to take a full day to train on these 32 best commercially available GPUs, probably P40 or P100, maybe. And now it trains the same accuracy, just within one afternoon with just one eighth of a TPU pod, which is pretty exciting. Okay, so it's a little wrap up. We covered a lot of stuff. We mentioned in the 4-dimension space of the algorithm and hardware, inference and training. We covered the algorithms for inference, for example, pruning, quantization, WINOGRAD convolution, binary, ternary, weight sharing, for example. And then the hardware for efficient inference, for example, the TPU, the ASIC TPU, that take advantage of integer 8, and also the my design of EIE accelerator that take advantage of the sparsity. Anything multiplied by 0 is 0, so you don't store it, don't compute on it. And also the efficient algorithm for training, for example, how do we do parallelization, and the most recent research on how do we use mixed precision training by taking advantage of FP16 rather than FP32 to do training, which is four times saving in energy and 4 times saving in the area, which doesn't quite sacrifice the accuracy you get from the training. And also Dense-Sparse-Dense training using better regularization, sparsity regularization, and also the teacher-student model, right? You have multiple teacher neural networks and have a small student network that you can distill the knowledge from the teacher neural network by a temperature. And finally, we covered the hardware for efficient training and introduced 2 nuclear bombs. One is the Volta GPU, the other is the TPU version 2, the Cloud TPU, and also the amazing Tensor Cores in the newest generation of NVIDIA GPUs. And we also reviewed the progression of a wide range, the recent NVIDIA GPUs from the Kepler K40. That's actually when I started my research, what we used in the beginning, all the way to, and then K40, M40, and then Pascal, and then finally the exciting Volta GPU. So every year there is a nuclear bomb in the spring. Okay, a little look ahead in the future. So in the future of the city, we can imagine there are a lot of AI applications used in, say, smart society, smart care, IoT devices, smart retail, for example, the Amazon Go, and also smart home, lots of scenarios. And it poses a lot of challenges on the hardware design that requires the low latency, privacy, mobility, and energy efficiency. You don't want your battery to drain very quickly. So it's both challenging and very exciting area for the co-design for both the machine learning deep neural network model architectures and also the hardware architecture. So we have moved from PC era to mobile era. Now we are in the AI first era, and hope you are as excited as I am for this kind of brain-inspired cognitive computing research. And thank you for your attention. I'm glad to take questions. We have 5 minutes. A question? Architecture, yeah, some of the ideas are pretty good. I think there's opportunity. Yeah. Yeah. The question is, what can we do to make the hardware better for Oh, right. The question is how do we challenge the challenges and opportunity for those small embedded devices to run deep neural networks or in general the AI algorithms? Yeah. So those are the algorithms I discussed in the beginning about inference. Here, these are the techniques that can enable such inference or AI running on embedded devices by having less number of weights, fewer bits per weight, and also quantization, low rank approximation, the small matrix, same accuracy, even going into binary or ternary weights, having just 2 bits to do the computation rather than 16 or even 32-bit, and also the WINOGRAD transformation. Those are also the enabling algorithms for those low-power embedded devices. Okay, the question is, if it's binary weight, the software developers may be not able to take advantage of it. There is a way to take advantage of binary weight, a paper in XNOR. So in one register, there are 32-bit. Now you can think of it as a 32-way parallelism. Each bit is a single operation. So say previously you have 10 ops per second. Now you get a 330 ops per second. You can do this bitwise operations. For example, XNOR operations. So one register file, one operation becomes 32 operations. So you can. There's a paper called XNORNet. They very amazingly implemented on the Raspberry Pi using this feature to do real-time detection. Very cool stuff. Yeah, so the trade-offs is always the power, area, and performance in general, all the hardware design have to take into account the performance, the power, and also the area. When machine learning comes, there's a fourth figure of merit, which is the accuracy. What is the accuracy? And there is a fifth one, which is programmability. So how general is your hardware? For example, if Google just want to use that for AI and deep learning, it's totally fine that we can have a fully very specialized architecture just for deep learning to support convolution, multi-layer perception, long short-term memory. But GPUs, you also want to have support for those, scientific computing or graphics, AR and VR. So that's a difference, first of all. And TPU basically is an ASIC, right? It's a very fixed function, but you can still program it with those cores instructions. So people from Google smartly designed those cores granularity instruction. For example, one instruction just load a matrix, store a matrix, do convolutions, do matrix multiplications. Those cores grained instructions. And they have a software managed memory, also called a scratch pad. It's different from cache, where it determines where to evict something from the cache. But now, since you know the computation pattern, there's no need to do out of order execution, to do branch prediction, no such things. Everything is determined, so you can take advantage of it and maintain a fully software managed scratch pad to reduce the data movement. And remember, data movement is the key for reducing the memory footprint and energy consumption. So, yeah. NVIDIA's and Nirvana architectures. Actually, I'm not quite familiar. Didn't prepare those slides, so comment it a little bit later. No. Oh, yeah, of course. Those algorithms can certainly be applied to low power embedded devices. If you're interested, I can show you some examples of, where is that? Of my previous projects running deep neural nets on, for example, on the drone. This is using an NVIDIA TK1 mobile GPU to do real-time tracking and detection. This is me playing the nunchaku, fueled by a DJI drone to do the detection and tracking. And also, this is the FPGA doing the deep neural networks, pretty small, just this large, doing the face alignment and detecting the eyes, the nose, and the mouth at a pretty high frame rate, consuming only 3 watts. This is a project I did at Facebook doing the deep neural nets on the mobile phone to do image classification. For example, it says it's a laptop, or you can feed it with an image and says it's a selfie, has person, face, etc. So there's lots of opportunity for those embedded or mobile deployment of deep neural nets. I know there's a team doing that, but I cannot comment too much, probably. There's a team at Google doing that sort of stuff, yeah. Okay, thanks everyone. If you have any questions, feel free to drop me an email.